Okay, I'm back referring to this sheet here, examples of hypotheses that would require a two-tailed test. And the reason I'm going through this is because you need to know the correct information in order to choose the correct t-value from the t-table. We've already been through degrees of freedom. Now we're talking about the task at hand. The second hypothesis, or example B, Kansas City residents will consume a significantly different amount of meat annually than the national average. The population mean, or the national average, is 207.7 pounds. The null hypothesis is Kansas City residents will consume an equal or same amount of meat annually as the national average. The population mean is 207.7 pounds. There is no direction stated in those hypotheses, no direction at all. It simply says different. That means we're open to finding that Kansas City residents eat more meat than the national average. We're open to finding that Kansas City residents eat less meat than the national average, and we're also open to finding that Kansas City residents eat the same, an equal amount of meat as the national average. Let's assume that we were asked to test the null hypothesis at the 0.02 level. Again, that level is 0.02. That is area, that is space, that is size. That's the size of our tail, or tails in this case, the size of our critical region, the size of our rejection region. Those things all mean the same. So we can tell from our hypotheses that we need a two-tailed test because direction was not stated in the hypotheses. It simply said different. It didn't say more, it didn't say less, it simply said different. So because it simply says different and direction was not stated, we need a two-tailed test. That means the tail is going to be split evenly between each side of the distribution. If we were asked to test these hypotheses, or specifically the null hypothesis, if we were asked to test the null hypothesis at the 0.02 level, that means that for a two-tailed test, each tail equals 0.01. Since I know that the critical region, or these tails together, the critical region, even though it's two tails, I still refer to it as the critical region. These two tails together are equal 0.02. That means that the middle part has to be 0.98. Why? Because I know that the whole thing has to be 1. 0.01 plus 0.98 plus 0.01 is 1. Let's look at example C, and then we'll move on to two-tailed test. Example C right here. H1. Residents of the Crossroads District will walk a significantly different amount of distance per week than the entire Kansas City metro area. So we're setting ourselves up to compare a sample, residents of the Crossroads District, and we're going to compare them to a parameter, or with the population being defined as the entire Kansas City metropolitan area. So H1. Residents of the Crossroads District will walk a significantly different amount of distance per week than the entire Kansas City metropolitan area. Population mean is 3.2 miles. The null hypothesis, H0, is residents of the Crossroads District will walk an equal or same amount of distance per week as the entire Kansas City metro area. Population mean equals 3.2 miles. So again, this is a set of hypotheses that do not specify direction, all right? Simply saying different. Well, let's further assume that we were asked to test that hypothesis at the 0.001 level. Again, that amount, 0.001, that is the size or area of the critical region. That is the size or area of the critical region. This is how it would look like, or this is how the probability distribution would look like if we were to actually test the null hypothesis in this instance. We've been asked to test the null hypothesis at the 0.001 level. I also know from the hypotheses that the hypotheses do not specify direction, so I need a two-tailed test. That means two-tailed test means the critical region or tails are split evenly. The area is split evenly between the tails. So if it's at the 0.001 level and I'm splitting that area in half, this tail is 0.0005 and this tail is 0.0005. Since I know that these tails together equal 0.001, that means that this middle part has to be 0.999. That's how big this middle part is. 0.0005 plus 0.999 plus 0.0005 equals 1. Okay. I'm going to cut this segment off, but when I return, I'm going to switch to this sheet in order to demonstrate how the probability distribution needs to be set up for a one-tailed test. Once I'm finished going through these 4 sets of hypotheses, I will then return to the t-table just to be sure that we understand how to choose the correct t-value from that t-table. Again, you need to know degrees of freedom. That's already been determined. That's already been explained. You need degrees of freedom. That's one piece of information you need to know in order to select the correct t-value from the body of the table. The other piece of information you need is the task at hand. Now before, just as a little primer, before you chose the task at hand based on the size or width of your confidence intervals. However, further in this gray shaded area, you can also see 2 things that are referred to. 2 things are referred to, whether you need a two-tailed test or a one-tailed test, and that's really what we've been discussing in this particular segment, and also the size of your critical region, and that's indicated by heading as well, 0.001, 0.01, 0.02, 0.05, 0.10, etc. Okay? Two-tailed test, one-tailed test, size of critical region. It is the size of your critical region plus whether you need a one-tailed test or a two-tailed test that will dictate which column your table t-value will come from. So as I mentioned, I will cut this off for now because I have an appointment with a student from your class. But when I return, I will continue on by explaining some one-tailed tests and the use of the probability distribution when we need to conduct a one-tailed test, which will hopefully solidify your knowledge in terms of how to go about selecting the correct value from the t-table, and also how to set up the probability distribution in order to conduct a one-tailed, in order to conduct a t-test for one sample, because the problems that you're going to encounter will require exactly that. You will be required to do some calculations, and then in turn take those calculations and apply them to the t probability distribution in order to make the correct decision about the hypotheses, but more in a little bit.